Okay, so we have talked about different styles of design, and we have also looked a little bit at how we would decide the optimality of a solution, right? Or if you cannot decide on optimality, can you at least say whether one solution is equivalent to another or whether one solution completely dominates another, right? Now, in order to even get those solutions, just the RTL code that we have written is not sufficient, right? We need to be able to convert it into a set of gates, and that process, it is what is called synthesis. Okay. So, how does logic synthesis in our case work? Basically what it does is it converts the RTL, the register transfer level code that we are writing, into a gate level netlist, right, which is basically a connection of a set of gates. As part of this, there are multiple steps, one of which is called technology mapping, which actually lets us map into a set of gates that are specific to the technology that we are going to be looking at. And there is also this notion of optimization, which means that we can look at the code and we can try to improve upon it in certain ways, right. The exact nature of what these optimizations are, they are very similar to the kinds of optimizations we looked at when we were looking at, for example, C compilation, right. So, are there ways by which we can find blocks of code that are redundant or can be eliminated or can be pre-computed while you are actually performing the compilation step itself, right? And not just that, after you have sort of gone into some kind of an intermediate representation, what are the other kinds of optimizations that we can do? Things like Boolean optimization, FSM state optimization, all of those fall in this category, right? So, the general sequence of steps that are followed is something like this. You first have to parse your input. Parse meaning that it's a term used to indicate that we take the program that's written in some kind of usually text type format, right, which can be edited by human beings, and converted it into an intermediate format which is suitable for the computer to manipulate, right. Some internal data structures that are suitable for manipulation by the computer, but are probably going to be hard for humans to read and understand. So, once we have got this intermediate representation, we start with the high level optimizations, right, which could include certain things like the certain Boolean optimizations, state machine design optimizations, things of that sort. What kind of states to assign, what kind of encoding should be assigned for the states, all of that can be done here. You can do technology mapping, right, which basically says that at this point I now need to decide that, okay, I have these Boolean equations, how am I going to actually build them? Let's say that I have only NAND gates, right, I need to convert all my Boolean equations into some kind of a combination of NAND gates. If you have lookup tables inside an FPGA, then you have a bit more flexibility, but now should you be using 2 input lookup tables, 3 input, up to 6 input is probably allowed. So, how do you go about combining these different inputs in a way such that you get a good mapping of your equations into the hardware primitives that you have? Now, each and every one of those gates has a certain delay associated with it, which means that you can now start to perform timing analysis, which also means you can do timing optimization. Now, after you have done all of this, and this part usually, well, some parts out here tend to be an iterative process. You do some amount of optimization, you once again go back and you do some other higher levels of optimization. You may not come back to do technology mapping after that, but you might for example choose that instead of using DSPs for one part of or the multiplier hardware for one part of a unit, you use some other kind of lookup tables, right? Instead of using the registers, you might want to use a RAM block, a memory block, right, or the other way around. So, there can be some sort of iterative process that goes around over here and finally helps you to arrive at a solution that you are satisfied with. And once you have done all of that, you finally generate an output which is a netlist. Some kind of description, right, either and typically in a format that's readable to the computer and not so much for the human being, right, which tells the computer how exactly what gates are to be used and how they are to be connected together. So, what I'm going to do now is to basically take up a couple of examples, right, the parallel multiplier and the sequential multiplier, look at their code and sort of walk through the synthesis process for each of those and just look at some of the numbers, right. This is probably going to be a very high speed or a lot of information in a short amount of time, but take your time, go through, and we'll have more examples of these for you to sort of understand what it is that you need to appreciate as the primary metrics of importance over here. Okay, so I'm going to start by looking at the parallel multiplier that we started out with, right? As you can see, this is pretty much what we discussed earlier, right? We have a parallel multiplier where I have used a parameter to decide the width. In this case, I have set it to 8, right? And what I have over here is I have defined a variable in order to hold the partial products. As you can see, I have used a two-dimensional array, right, which basically can be indexed as partial products of I would basically give me the ith element of this partial product array. Now, the reason it's defined in this particular way and not by sort of having the square brackets width afterwards is because of a particular limitation of system Verilog syntax about how arrays can be passed into and out of modules, right. In some sense, this is more a question of how the compiler looks at the problem, because the same thing can be solved in different ways, and it depends to some extent even on which compiler and which version we are looking at. But this notation works for this particular problem at least, right. So what we have is a partial product generator that generates partial products and an adder tree that generates the result. Let's very quickly look at what the code for the partial product generator looks like. Slightly different from what I had discussed during the in the slides, right. What I have used over here is a generate statement, right, where I actually have an assign inside a generate for loop. So effectively what that means is that at compilation time this will get fully unrolled out into a set of, well, in this case, since width is equal to 8 different partial product assignment statements, right, rather than having an always block. Now those are choices. It turns out that iVerilog has problems if you put always blocks inside a generate statement in this form, or rather inside a for loop. So it's probably more convenient to have it using a assign statement in this way. You'll also notice that the final partial product corresponding to the MSB is done as minus, right, just to sort of make it easier to handle. Now interestingly, this entire module out here is basically a very compact way of writing partial products independent of whatever width is required. It's been nicely parameterized away. Now what about the adder tree? It turns out that yes, the adder tree also works in a similar manner. It's also parameterized. It takes the partial products as inputs and generates the sum, which is the final product, as the output. This is also written using a set of for loops, right. The first thing we do is that we have one for loop which basically initializes, takes all those partial products and puts them into a variable called stage sums of 0. This is just a copy. If you think about it from the point of view of hardware, nothing's really happening here. This is just sort of renaming the variable, right, and the compiler will hopefully figure that out and not try to create any hardware for it, right. It shouldn't, because there is really no hardware to create in this case. It's just a copy of a signal that already exists. What happens out here? We have a for loop that goes across the different number of stages, and we have another for loop that basically goes across the entire width. But now it does it a little bit more cleverly. What it says is, it first checks whether we have reached up to the end of, at each point we are basically trying to take 2 inputs at a time and reduce them, which means that the very first time on stage 1 I need to go up to width by 2, right, and basically pick up the value at I into 2 and I into 2 plus 1. But now I have reduced the total number of my inputs itself to n by 2 by the time I have gone to stage 2. In stage 2, I will only go up to width by 4, width less than stage, where stage is equal to 2 is width divided by 4. So it only goes up to the first n by 4, but that's because there were only n by 2 values in the previous stage, right. So stage 0 had n values, stage 1 has n by 2 values, stage 2 has n by 4 values, and so on until I finally come down to 1 value. And that's essentially all that is happening in this set of loop out here, right. We finally have a sum that gets generated, and that's basically the output of my module. What does the multiplier itself look like? It instantiates the partial product generator, it instantiates the adder tree, it takes the sum coming out of the adder tree and connects it up to the product, which is the output of the partial product generator. So I would like to have a test bench that checks this. So what I do is I have some kind of a test bench along these lines, right? I basically have a parallel test bench which instantiates my parallel multiplier and then goes through this process where it can run n test cycles. I can define a parameter to specify how many tests I want to run. It generates random values as inputs, right? Waits a little bit of time, this is just for the simulation, and then finally checks whether the product that got obtained is equal to the expected product. Now how do I get the expected product? Well, I just use the fact that this is Verilog and I can compute A star B, right? So if it doesn't match, I basically increment the error count and finally I can print either a failed or passed message based on how the system worked. Let's very quickly try this out. So what I have done over here is I am using the iVerilog simulator. I am passing the flag G2012 to indicate that it needs to account for the fact that the code is written in System Verilog version 2012. It's not as though I'm using any of the fancier versions of System Verilog, but some of the aspects such as even how arrays can be passed into modules and so on were formalized in System Verilog 2012. So without this flag, it actually has difficulty compiling it properly. And once I have done that, right, so iVerilog, just like in the case of a C compiler, I would generate an executable. iVerilog actually also generates an executable. By default, it calls it a.out. You can rename it to anything else that you want. But when I run the a.out, what happens is that the Verilog simulator actually kicks in and simulates and prints out a message. In our case, it actually prints a very simple message, right? It basically says it passed 100 tests, okay? Now, how do we know that this even worked correctly? Well, I can intentionally go in there and make a mistake, right? So for example, one of the choices could be this line out here, line 17 that I have, right, was put in here to handle the case where I have a negative multiplier, right? And if I don't have this minus sign and if I remove this, what I should find is that whenever my multiplier is negative, my result goes wrong. So let me try that out. And sure enough, I find that, wherever I have a negative multiplier out here, in all of those cases, my final result ended up coming out wrong, right? So it's always good to make sure that your test bench actually does catch scenarios with error. So in fact, one of the approaches for design, which is called in some sense test driven design, is to say first write out your tests, make sure that all the tests fail, and then start adding code which passes one or a few tests at a time, so that you know exactly which code has solved which problem, right? Ideally, it shouldn't be that one change in the code that you make solves all your problems at once. If it did, it probably means that either your other tests were redundant or it means that you are not really testing the right things, right? In this case, I had a very clear scenario where I could say that by changing this, I know that it's going to fail for negative values of multipliers. And by fixing that, yes, I get the point where it basically passes all the tests, okay? Alright, now I have similar code corresponding to a sequential multiplier, right? This code is a little bit more involved. Right now I'm not walking through the entire testing process, but I'll walk through how the code works, right? The code itself looks more complicated. As you can see, it has a clock and reset as inputs. It has the multiplicand and multiplier as input, and it also has the product as output, which is the same as what the parallel multiplier had. But apart from the clock and reset, it also has one input signal called start and an output signal called done, right? Now, why is this needed? Because a sequential multiplier takes many clock cycles in order to perform its work, which means that even in my test bench, I would have something which basically says, okay, give start equal to 1, after a short while make start equal to 0, and then wait for done signal to become equal to 1, right? that's essentially the primary difference between the sequential multiplier test bench and the parallel multiplier test bench. They more or less work exactly the same. Okay. So roughly speaking, how does the sequential multiplier work? As we saw, there are some control signals, right? The clear product, shift product, add multiplicand, and a bit count, right? And in this case, a bit count, I have set it using this function $CLOG2, which basically means take the logarithm to base 2 of width and take the ceiling of that if it's not an integer, right? So for example, if width was equal to 8, $CLOG2 of that should become 3. Now strictly speaking, you only need a 3:0 bit count in order to count the number of bits that you are going for. I have just added one over here. It's not strictly necessary. The compiler should in most cases actually be able to eliminate that, seeing that it's never being used. Okay. Now I also have my data path, and as we saw, I have a multiplicand register. I don't have a multiplier register as such because of a certain trick that you will see in a moment. I have a product register, and I have another piece of logic that tells me whether the sign adjustment is needed. This is basically for the negative multiplier case. Now this code that I have over here is unnecessarily complicated, right? And what I mean by that is, if you look at how this code is implemented, it basically implements checking the value, then adding, then shifting, then if necessary going into a separate state for adjust. In some sense, it was basically written this way more or less to demonstrate that yes, you can have a state machine to do this, but is it the most efficient way of implementing a sequential multiplier? Certainly not, right? It is possible to have a more efficient sequential multiplier. That doesn't matter. What I'm trying to do is just sort of illustrate one way of designing. Now okay, so we have the data path registers defined. Now I can define the FSM states, and here we make use of features of system Verilog. We have a type def, right? We can basically define a state type which has all of these values. We don't need to assign values 0, 1, 2 and so on. By default, yes, Verilog does automatically go through as 0, 1, 2, but it will also, as we will see later, do some kind of reassignment where necessary. So what does our design look like? We first have a control FSM, and FSMs, as we already know, are sequential elements. We have a clock. What they need to do is all of these values, the state as well as the bit count, clear product, shift product, add multiplicand, all of these need to be processed as part of the state machine. Done is an output, and so is the sign adjustment needed. Well, that's also a sort of control signal, right? And if you look at it, all that it says is whenever we are in the idle state, if the start signal comes, then send out a clear product signal, which basically is to sort of remove the previously computed product, right? Because what we are doing is we are holding on to the last computed value until I get a new set of values to compute upon, right? So whenever I get a new start signal when I am currently idle, I will clear the product. Well, I will only send out a signal to clear the product. The actual clearing of the product is done by the data path. When I go into the load state, I will reset the clear product signal, and then I'll reset the bit count and also check whether eventually I would need to adjust for the multiplier or not, right? I'm just recording this right here. But after that, I'm essentially going to go through and interesting, I'm checking the product reg of 0, not the multiplier reg of 0, right? And this is because of a trick that we are using. Basically what we are saying is I'm going to be loading in the value into a 16-bit product. I will put the multiplier into the bottom 8 bits, and I will keep adding the multiplicand in the higher order bits. So effectively what I'm going to be doing is I will add something into the higher order bits and then shift to the right. Rather than shifting the multiplicand each time, I'm going to just keep shifting the product in place because I already have a 16-bit register available for it, right? So this is sort of a small optimization in some sense in terms of how we write and model the code, but it doesn't fundamentally change anything. If you wanted to write it such that you actually wanted to shift your multiplicand each time and add it, you could do that as well and it would work perfectly well, right? Okay, so what we do is we check if the product requires addition. If so, we go to add, and we activate the add multiplicand signal. If not, we straight away jump to a shift state. Okay. Now, if I wanted to add, I would reach the add state where presumably the data path would have added something, but after that I move into the shift state, right? And in each case shift product must be equal to 1, so that I basically have the shifting being done in the shift state. After I have shifted, I need to basically go and check, either I go back and check the next bit, or if I have reached the last bit, I go either to an adjust state or to a complete state, right? And this adjust state basically adjusts for the negative multiplicands, right, which again we will handle in the data path, and then finally goes back to the complete state and says, okay, everything is done, now go back to idle, after making done equal to 1 for a single clock cycle while I am in this state. So the state machine, as you can see, actually is not doing any work. It's not adding numbers, it's not telling you what to do with the operations, it's not even telling you how to clear the registers, but it's generating all the signals that are required. The data path logic comes immediately after that. It's also a sequential block, because as you can see, we are manipulating registers. There's a product register and a multiplicand register that we need to play around with. Okay. So now we see that, if the clear product signal is high, then I need to basically load the multiplicand into the multiplicand register and load zeros into the product register. But instead of just zeros, I'm loading in the multiplier into the bottom half of the product register, so that I can use it. I can basically look at it one bit at a time, right? Then I basically go through to checking, is the add, so I'm not in the clear product state, so then am I supposed to add a multiplicand? If so, then well, let me either do the regular addition, or if I am in the complete state, that is in the final state, I need to do a subtraction. And at every other thing, if the shift product signal is high, I basically need to do a right shift of the product register. By repeating all of this n times, right, I should find that my overall system successfully multiplies the different values together, and I have a test bench that basically will test it out by doing the same thing out here. Okay. So the behavior of these works exactly the same.